Hello everyone, Professor Dustin here, and this video I'm going to talk about combinations of resistors. So this is a situation where you have a circuit with a number of different components in it, and for right now we're just going to isolate circuits with just resistors, but more than just a single resistor. So let me just remind you what a picture of a single resistor in a circuit looks like. So I'm going to start by drawing a EMF or a battery source of some kind, and then I'm just going to connect some wires to a resistor. And so that squiggly line like that is a resistor. We'll call that R, and we'll usually call this something like V to denote the potential. So in a circuit like this, the effect of the resistor is very simple. It allows us to calculate the current using Ohm's law. Simply V equals IR. But in most real-life circuits, we don't just have a single resistor, we have a number of different resistors, and so really the question we'd like to answer is, what is the current through a particular set of resistors? Of course, we could say we know the current, we'd like to know what the potential is, or we'd like to know what kind of resistor we have to put in the circuit to get out a certain current. There's any number of questions we'd like to ask, but we'd like to ask these questions of circuits with more than one resistor in them. So I'm going to talk about two specific examples of this. First, resistors in what's called series, and then what's called parallel. So let me give you the typical example of a set of resistors connected in series, in which the potential is here, and we have three resistors, R1, R2, and R3. That's three resistors connected in series, and now let me get you a picture of three resistors connected in parallel. That looks like that. Potential there, R1, R2, R3. So you can see that these two circuit diagrams are quite a bit different in the effect the resistor likely has on the current, even without doing any mathematics. The potential here, there's a drop across this as the current crosses the battery, and as the current flows, it flows through one resistor, through the second, and then through the third before getting back to the battery. So series means as like a mathematical series or a series like a novel series, you go from one to the next to the next. The current goes between all three. For the parallel one, parallel here means something like parallel lines. The current leaves the battery and then chooses which direction to go down, and how it chooses depends on what the exact resistances are. So every part of the current goes through every resistor for the series, but not every charge in the current goes through the resistors. So how are we going to take that into effect when we try to calculate what is the current through the circuit? Well, it turns out we can derive this just by using Ohm's law and the basic principle of potential drops. So as the current travels around the circuit, there are potential drops associated with every element of the circuit. For instance, the battery is not actually a potential drop, it's a potential gain. As the current crosses the battery, it gains a potential V. But as it goes through the circuit, it drops a certain potential here because of Ohm's law. So it drops a certain potential here, and it drops a certain potential there, and the total gain here has to be equal to the total drop here. So we can just add up the drops across each of the resistors to get the total. So that's the total drop across each resistor has to be equal to the total gain across the battery. So now we can replace everything in here with what's in Ohm's law, which looks like that. Now I knew what to put here, V equals IR, because this is the potential drop across the first battery, so obviously that should be R1, that should be R2, that should be R3. I'm actually not sure what to do about that current, and further, I don't know what this actually means over here either. Which R am I talking about? So first let's talk about the current. If there's a current which travels through the battery, because of the conservation of current, there can never be any current loss as the current travels through the circuit. So the same amount of current that goes through the battery has to be the exact same that goes through R1, has to be the same that goes through R2, and the same that goes through R3. There can't be any differences in current because charge is not lost in these currents. So each one of these I's is exactly right. It has to be I, the same I everywhere. So because we have an equation with the same variable in every term, we can simply divide by I and cancel it out of every term. And that simply gets us that this R, whatever it is the sum of each of those R's. Okay, fine, but that doesn't really tell us what this R represents, but actually we know that since it came from this version of Ohm's law, this is actually the R for the entire circuit. Because I started by writing V, and then I said, okay, that's IR, but this R is actually this combination of resistors. So this is Ohm's law for the entire circuit all at once, for that V, for the I, and whatever this R is, which represents the sum of all the individual R's. So we usually call that the equivalent resistance, label it EQ. And so now we have a way of finding that equivalent resistance, which is just the sum of the individual resistances. We know what the current is because it's the same current that goes all the way through the circuit, and the battery is just V. So we basically simplified our problem down to a system of 3 resistors, down to just a system of 1 resistor with our equivalent. So what I'm saying is these two pictures, this guy and this guy, are exactly the same if our equivalent is given by the sum of the individual resistors. So that answers how do we deal with a series circuit. We can replace all the resistors in series with a sum of the individual resistors. Very simple. Can we do the same thing with the parallel circuit? Now I'm going to go on to another sheet to show you how you can do this. Okay, so here's our circuit with 3 parallel resistors in it with the same battery. So I'm going to play the same kind of trick. I want to combine all of these together in some particular way by using Ohm's law. So what I'm going to do first is just write down Ohm's law for each one of these cases. So what I've done is I've written down for the total battery, so remember this is V equals IR, this is some current which is going through the battery, and whatever the end resistance is going to be. I don't know what that's going to be at this stage, but I can just call that R equivalent. That's the thing we actually want to calculate eventually. And then for each one of these resistors, I've written V1 equals I1R1. This is because unlike in the first case when I knew the current went through every resistor, I'm not sure what to do in this case. The current could be different because the current is being split among each resistor. I'm not sure what to do about that, so for now I'm just going to write V1 I1 and R1 V2. That should be I2. V3 equals I3 R3. So let's think about what conservation of charge would mean in this case. In the last case, I knew that the current going through every resistor was exactly the same, but that's definitely not going to be true here because some current is going to go there, some current is going to go there, and some current is going to go there. But I can still use conservation of current because I know it's still true. For instance, I know that if there's a current I, which is that I going through the battery, then if some current I1 goes through there, and some current I2 goes through there, and some current I3 goes through there, then the sum of all those 3 currents has to add up to be the current I. Because of conservation of current, I can't have charges which leave here and do anything besides either that or that or that. There's no fourth path, charge can't be lost, so everything that leaves through the battery has to go through one of those guys. So I can write the following equation. I is I1 plus I2 plus I3, which seems simple, but that's going to let me find a relationship between these 4 quantities. Next step is just going to be solving for each one of these guys, I1, I2, and I3, and putting them into that equation. Okay, that's pretty simple. Every term is just V over R due to Ohm's law. So this is looking pretty good because I've gotten rid of all the currents, but I still have a bunch of potentials which I don't know. It appears that I do not know what V1, V2, and V3 are and how they relate to V. So let's just think a little bit more carefully about how conservation of energy works in this circuit. So recall that we can write the electric potential energy as U is simply Q times V. So if we're talking about conservation of energy, we want to talk about U, but if we're talking about conservation of energy for like electrons, each electron individually jumping over this battery, then we could talk about conservation of V, and that works the same way as conservation of U. So what happens to the potential as you cross different points in this circuit? So for instance, when you cross from that point to that point, you cross a potential difference of V. That's the only circuit element you cross, and so that's the potential difference between here and there. But the wires transmit equipotential surfaces. So as long as I move along a wire without crossing another circuit element, I have the same potential drop. So if I go from here, cross V, I now have a potential drop of V. But if I keep going along this wire, then I still continue to have a potential drop of V anywhere I go as long as I don't cross the circuit element. Same deal with going from here down. That's a potential drop of 0 because I haven't crossed any circuit elements. So what happens if I go between this point, right there, call it A, and this point, call it B? So the potential drop across those two is obviously VAB is V, the potential drop of the battery. But I can also measure that potential drop by going the other way from A and crossing that resistor to B. What's that potential drop? That's V1. So I have two ways of writing the potential drop between A and B. It's V or V1. That means that if that's the same potential drop, V has to be equal to V1. And it shouldn't take much to convince you that I could do it from here to there. I could do it from there to show that V is equal to V2. And I could go from there to there to show that V is equal to V3. So I've just demonstrated that all the potential drops in this circuit are exactly the same. So now I'm going to go back up to this equation, put in V for every one of those, which is that, and now again I have a case where every term has the same variable in it, so I can divide this whole thing by V and get my final answer. And that is that the inverse of the equivalent resistance of this circuit is equal to the sum of the inverses of the equivalent of the resistance of each resistor individually. So this is a little bit more of a complicated equation to use because you can't just sum up the resistances. You have to first take 1 over the first resistance, add 1 over the second, add 1 over the third, and then you're not even done. You have to take that entire combination and do 1 over it in order to get the actual equivalent resistance. So it's a little bit harder to use, but in form it looks very similar. The equivalent resistance, and that is the resistance which would go into an Ohm's law, like V equals IR equivalent, for a parallel circuit is the inverse of the sum of the inverses of the resistance. Okay, great. So these are the two basic ways you can combine resistors. Now, of course, you can have some series and some parallel circuits as well, but that's just individual parts being parallel and individual parts being series, and you can combine them in different ways. And I'm sure that you'll see some examples of this in your class or in the homework. Great, so thank you very much for watching. This has been an introduction to circuits with series and parallel resistors. Thanks for watching.